All right. Today we're going to start chapter 2. On Friday, Dr. Easton went over a lot of the nomenclature and items in chapter 1. Your homework for chapter 1 will just be probably, again, some vocabulary and definitions, a few concepts, and that will be posted in Pearson, Mastering Chemistry, and that will happen within the next few days. And then we'll get started on chapter 2 assignments here soon.
Can you send out that code for
I
the
will
website?
send out the code,
Heaven
yes.
needs to buy that.
Yes, I will send that out, definitely. Okay, so chapter 2, we're going to be talking about weak interactions in aqueous systems. What's aqueous?
Water, H2O.
Water, that's right, water-based, hydrophilic, okay? All organisms are made up of 70% plus water, so it's no wonder why we have molecules that love water and why we have molecules that hate water, okay? Hydrophilic and hydrophobic, and we'll talk about both of those as we go along. Mostly today we're just going to be talking about hydrophilic interactions. Non-covalent, what is covalent again?
Sharing electrons.
Sharing electrons, okay? So non-covalent would be
Ionic.
or
Not sharing electrons at all.
or not sharing electrons. So what type of interactions might some of those be? Okay, dipole. In general, what I would be stating is they would be considered electrostatic, okay? So really what we're talking about are non-covalent electrostatic interactions between molecules and also within molecules. So we talk about inter and intra both. Okay. So inter is between or more molecules or ions, and intra would be interactions that are within the same molecule from different regions of the molecule, okay? So looking at inter and intramolecular non-covalent bonding type interactions, these are actually quite prevalent and very important in many biochemical applications and biological molecules. Let's take a look in your book. Your first figure that's actually in your book shows the human growth hormone, that's HGH, the human growth hormone binding to the receptor. And that type of binding interaction is non-covalent type interaction. Why would you think it would be designed like that? Why do you think it would be designed as a non-covalent interaction? Oh, so not only can it bind, but also so it can be released. What an elegant design to be able to do that with minimal energy input, right? Minimal energy input, minimal energy output to have that type of a binding occur. The human growth hormone, that is a protein or a peptide. So let's review what is a peptide? What's a peptide? What's it made from?
Is it a chain of proteins?
Very good. It's a chain of amino acids. Okay, so a peptide. Really in a polymer form, right? So if we look at an amino acid, I'll just draw some generic amino acids here. start to pair together, how does this reaction happen?
Is it a dehydration?
It is, which is also called a condensation reaction, okay? So this nitrogen bonds to that carbonyl, and then this is where the condensation happens, and that is lost as water, okay? So your peptide bond is formed here. When peptides begin to get longer, become polypeptides, and they start to develop more interactions, they can become what? Polypeptides, and also then become proteins. Okay, can also become proteins. The human growth hormone is a specific hormone called a mitogen, M-I-T-A-G-E-N, mitogen. This one is made up of 191 amino acids. It's pretty big, okay? Mitogen is responsible for cell proliferation, for cell division, and mitosis, okay? So it induces mitosis, hence why it's called a human growth hormone, okay? But those non-covalent little electrostatic interactions are like tiny magnets. Literally, your body is working on all these tiny magnetic interactions, and that's how ions are passed through our bodies, and we'll talk a little bit about that. But that's also how molecules are attracted to one another non-covalently. Any questions on that? Does anybody know what receptor the COVID-19 binds to?
ACE2.
The ACE2 receptor. ACE2 receptor is involved in what? What's it involved in? Your cardiovascular system. That is why COVID-19 can affect the heart, is because of that ACE2 receptor binding. Okay, it's very interesting, that life cycle. We can talk about it more, but it's pretty fascinating. Here's the X-ray crystal structure. We talked last semester in Organic 1 about the benefits of X-ray crystallography, and this is one of those big benefits where we can crystallize proteins and we can see how specific substrates bind to those proteins non-covalently. We can design drugs and look at X-ray crystallography images like this and look at the specific interactions between the amino acid sequences and actually how the drug binds into the cleft of the protein to interrupt those specific functions. I worked on the Calitra project at Abbott, which is the anti-HIV compound. I was able to see some of these images of the HIV protease and to see how that inhibitor worked. Really cool stuff. If we didn't have X-ray crystallography, we would be pretty far behind. NMR is actually being used now for larger macromolecules, but this is unparalleled. Caleb?
How and why do we choose colors for X-ray crystallography structures? Because aren't the images we get black and white?
Don't you think it would be boring though?
Well, do you have like, is it actually that color?
No, sir.
Oh, okay.
No, it's definitely not that color. We do this just for enhancement. It's the same way when you get pictures from Hubble in outer space, all of those are enhanced images. None of those colors are actually true.
Oh no, I know, but I mean, like, does it actually have a color, or is it so tiny that we can't tell? Or?
I have no idea.
Oh, okay.
I have no idea. I would say that we've probably not generated enough crystalline material of some of these things to see the color. Maybe, but most colors in organic chemistry are not that exciting. So it's not like inorganic, right? Okay, so this shows the structure of the human growth hormone receptor binding, and we can zoom up and see these interactions even more closely, so you can actually see what amino acid residues are actually being affected. So let's think about this from a drug standpoint, okay? let's say that you have a whole library of compounds in your repertoire, and you're going to go through and you're going to scan all of these compounds through assays, okay, for binding. And eventually you find one that shows that it has a pretty good binding coefficient. It is binding. So what they will do is they will co-crystallize that compound with the protein or enzyme, whatever they're looking at. And they will co-crystallize them together. And they'll get an image like this. The X-ray crystallographer will be able to show the intermolecular distances between these non-covalent interactions and show you where that binding is actually taking place between the drug and the amino acid residue of that particular cleft. How might that be manipulated? How might they make that non-covalent interaction a little bit better?
By getting it closer together?
By getting it closer together. How might they do that from a medicinal chemistry standpoint? What might they do to that lead molecule?
I'm gonna say stereochemistry and do something with stereochemistry.
Okay, maybe change the stereochemistry. What else?
You could charge it.
Okay, maybe make it charged. What else? How about changing a functional group? Maybe make a functional group that actually undergoes hydrogen bonding to another residue. Maybe you make it to where it can actually interact more than 2 or 3 times. Maybe you make it interact 5 or 6 times to other different residues of amino acids. These are the ways of medicinal chemistry. These are how they make drugs better and more effective. And it's a molecular warfare, essentially. Riley?
When you have like 2 substances like this, where you have nitrogen that's binding to your receptor, isn't it usually like binding multiple times already? Because if it was just binding once, wouldn't that be very weak?
That's correct, yeah. So you are correct. We're talking about multiple binding sites within that particular receptor. I'm talking about a drug inside of a protein or an enzyme or something like that to shut down the function of that or to manipulate the function of that. But yes, you are correct. Yep. Any other questions? Good question. Okay. Most of the time, we're talking about interactions between oxygen, nitrogen, and hydrogen. Okay? Those are your primary typical interactions when we're looking at proteins, peptides, and small molecule therapies that are manipulating those sites and or receptor binding. Okay. Take a look at the actual energies. This is also recorded in your book of these types of non-covalent bonding interactions. We know that London forces or van der Waals interactions are really those weaker interactions. What do you notice on this? What do you notice on this?
That sugar is about 100 times more energy efficient than ATP.
Okay, but if you think about the combustion of glucose, Avery, what are you actually doing to the bonds in glucose up there? What are you actually doing to the bonds if you combust anything?
Oh, you're releasing energy, aren't you?
But you got to put some energy into it. But what's happening to the bonds?
You're breaking.
You're breaking the bonds, right? So naturally, covalent bonds and covalent interactions require quite a bit of energy to put into them. Now, for combustion, you're going to get energy out because you're forming more stable complexes, carbon dioxide and water vapor, right? But what do you notice about the non-covalent interactions as compared to that?
Non-covalent is lower. than
Significantly lower. Why? Why?
Because every time it breaks something, you have to put the same amount of energy into it.
It all comes back to energy. imagine if it took that much energy for you to have HGH bind to that receptor, right? Versus a very minimal amount to do the binding, right? And to do the release. And it's all about conserving energy. That's really all it's about. Okay? Thermal motion. This actually really struck me. Thermal motion. Why should that strike your fancy?
I was noticing how the sulfur used in the hydrogen bonds are not a lot higher, but they're like significantly higher than the thermal motion. I was noticing that.
Yeah, but there is a reason for that. A very divine design, a very specific thing. What is 37 degrees Celsius in Fahrenheit?
Body temperature.
98.6 is body temperature. If hydrogen bonding was anywhere closer to our body temperature in regards to breaking it, what would happen? We would die. We would die, okay? And that's why when we get a fever that is above like 105, this starts to get dangerous because you can start unraveling proteins and things can start to break down, okay? Because that hydrogen bonding is right there. Now, there are also hydrogen bonding interactions in other biological molecules, not just proteins. And there is also a very specific reason why they are right where they are. And I do think that it's a very unique and innate design. And for me, that really proves we have an awesome, all-knowing God. And that is one of my most favorite things in science that I've always gone to, is where the energy level exists for hydrogen bonding interactions. Let's take a look at some of these before we get too far into this. Let's take a few moments. Why don't you get into groups of 3, groups of 4. Why don't you try and draw out some intermolecular force interactions without using your book and see how many of them you can come up with. Let's do that. Let's do that. Non-covalent intermolecular forces. Don't use your book, Ruth. See how many you guys can come up with. I've already given you a few, but I want to see how many you can come up with. And I also want to see what pictures you draw too, and I'll come around. Avery.
And then obviously you got the light, it can, it's not common for it, but like, it can obviously overlap.
I know that water might like
Yeah,
dissect because it's in
and say you have like hydrogen by positive.
it's more negative up here, it's positive down here.
I'll walk around and see what you guys come up with. Oh, no.
I saw the.
Cody and Cody, what do you think? You're gonna do both. You're gonna write and you're gonna draw pictures of what interactions you can come up with. Non-covalent interactions.
Oh wait, she's not touching. This one you don't have like,
She's got the charge.
Red pie to pie as well. Yeah, that one would be.
Really close together. Yeah.
How's it
Good,
going?
great, Maxwell. Thanks for your face.
Okay.
That's okay. That's looking good. Okay.
Together.
Okay.
Well, because it's just electrons around and then like. And then something that would
So that the low energy states when they're connected, like less versus their attracted colors.
Anything that wants
No, they.
well, what's a hazard?
Some of you may come up with, non-biological type molecules, and that's okay. I'm just more concerned with you trying to figure out what molecules you can do or what functional groups you can use to have those types of non-covalent interactions.
Because if there's nothing to do with negative and
Positive there. Yeah.
And then iodine and iodine molecules actually bind the wall.
Like a.
Yeah.
That's like why.
There's like defining hydrogen markers, is that a covalent
Yeah.
And then sodium and chloride. No, there's some more. It's an iodine and water. Charge.
Okay, I'm trying to think of an example of a dipeptide.
I want you to do your best to try and draw accurate chemical structures as much as possible. At least functional groups. I think that you're capable of doing that.
I'm trying to think if the molecule.
And you can keep it simple. Just try and keep it simple.
Say you got like someone there, you can also interact with this.
They're all quiet, like.
I remember taking most of those
you got that. A molecule with a dipolar, trust me, I know you can come up with that.
Oh, you mean like, oh.
I'll give you a hint, Ruth. Your body's made up of 70% of this molecule.
I mean, I knew that one was pretty good. And then we potassium and.
I can't think of an example for this one.
Keep after it, ask your neighbor.
Yeah.
For you who've had organic recently, you might also think about molecules that can have dipoles that can, or molecules that don't have dipoles that can have dipoles after something happens.
That's what I can't think of an example. I don't know why. I wonder if he.
It's been a hot minute, it's been over like a year.
I like what I'm hearing, there's good conversation, keep it up. You guys over here are a little bit quiet.
Yeah, we went about as far as we can, I think.
You went about as far as you can.
I think so.
Okay, I'm gonna come see what you got.
Really like, no, yeah.
Yeah. I mean, I was good idea.
Okay, so you're okay here. I don't like necessarily the portrayal of it,
Yeah,
but
yeah.
that's okay, you're getting there. Okay, alright. Okay. Okay. That's okay. Okay, if you think about charge, right? A cation and anion, right? Okay? But we won't have solid sodium chloride in our body. So that will kind of give you a hint as to maybe how could these be separated but still be stabilized? How could sodium and the chloride ion be separated but still be stabilized in our body? Think about that. That would also give you another one if you thought about that. Think about ion transport. Think about ion stabilization and ion transport. But the question is, how are they stable as individual ions? How can a cation pass through and an anion pass through separately in your body? Don't answer it out loud, just think to yourselves and then try and write it down. Try and give a picture of it. Draw a picture of it.
Yeah. Like it has to
Because, I mean, that's how they would live.
There's more negative on one side and the other. Yeah. Is that how you can separate those splits into positive?
But it's not, you know what I'm talking
Like
about.
it's still
You're in the
stabilized,
same
like if
area.
you solve salt and water, it's still stable. Salt and then, so if you have a comparison, I use stable water, I like this too. Positive, negative, they were, you take this apart, how do you
This stuff like that.
well, when you dissolve it, water surrounds it.
So I'm saying that it starts out as NaCl because it's sodium chloride, but is that why?
It's one of those,
Hydrogen in our body are still live together because they're gonna have two different charges but kick us.
This is where I thought.
Yeah.
How do we get iodine salt? Like iodized salt, how do we do that typically?
I don't think it's chemicals.
So is it not?
I think it's
The worst
makes
draw.
you-
Is it just iodine in our salt?
No, that's a good question.
Yeah.
What do they mean by iodine? Like,
That's what he's asking.
That's what he's asking.
I'm just gonna go for it.
That's off topic. Get back to work.
Just once upon
maybe they like purified it and then re-ionized it.
All right.
What did you do?
What do you guys got?
She was starting
And
like.
it is positive, right? But okay, let's say it's solvent water, Na plus CO minus. The positive Na.
Okay, so you're on the right track here, but you just gotta think about like, how are you going to use this dipole to induce another dipole? So,
I've never seen a sugar on this.
that's okay, that's all right. I know some people are gonna be rusty. I know this. It's okay, I know this,
Yeah.
okay?
Need
All
an
right,
example of a
so
charge.
you know that HCl has a dipole, right? Okay, so think about this. How might HCl gas in a concentrated form be attracted to more HCl gas
These chapters are kind of, like, they're not.
How might that happen?
They're only like 20 points. but
Put some,
the content
put
is
some
so
partial
easy.
charges on
And
it.
it's too on.
So imagine if you got it so concentrated that it started to
Reactions that make proteins.
precipitate or become a liquid.
Hydrogen, electric bond, disulfide,
How might that happen?
non-polar.
Do we have gases in our
They're
body?
attracted to each other because
Yes.
we
Yes,
lowest
we do.
energy, like the lowest energy combination
Yeah.
is the least amount of surface area touching.
Well, think about respiration,
The more they're
right?
touching each
You
other,
inhale
the
oxygen,
lowest energy
right?
state they're in.
There are gases
So
that
it's
can
not
get in
that
the body
they're
that are
attracted to
bad,
one another,
it's
Oh,
like
two gases.
nitrogen.
by everything else.
That can happen during like scuba
Throw some
diving.
iron in that.
Nitrogen
So I
can
have
build
what
up
I
and you
recall,
can get
because
Nitrogen
bad
is
that
that
nitrogen does
It
interact,
is.
it's not Van der
So
Waals.
that can be bad. But, I mean, we think about carbon dioxide, right?
So
Yep.
carbon's
So
Yeah, carbon
oxygen,
dioxide.
carbon dioxide.
I do have a question.
They know
So
another
this interaction
interaction,
is-
but they're not really attracted to each
So
other.
this is
It's
more
my understanding.
positive and then this would be more
Are you talking
negative.
about London
which is
forces?
positive. So wouldn't that,
Aren't you talking about London forces?
they make H2, right? Or
Are they?
am I totally wrong?
So,
Well, they're attracted to each other, but they're
you're
not
looking
really
at
attracted
sodium
to each other.
hydride,
Yeah.
but the issue with this is that these would react together to make a covalent bond. So, what I'm talking about is non-reactivity, only attraction.
Only attract, okay.
Only attraction, okay? But you guys are on the right, you guys are on the right, direction. You're
Oh gosh,
doing
and I'm
pretty good.
sitting right next to you, so they're gonna
Got
get.
water and
Oh, okay, that's a great example. Okay, so Caleb was saying
Those are the
DNA-based pairing, okay? If you're talking about guanine and cytosine, adenine, thymine, uracil, that's examples of hydrogen bonding interactions between the DNA-based pairs. That's a perfect example.
But
It's a
aren't they
great
also
example.
held together by,
I can see the
other
attraction
things,
there.
like, I think there's. I'm not sure, it's either, it's like dipole or ionic, I don't remember which one the book said. I think
Okay,
it's ionic.
okay,
I don't remember.
what else you got?
That's water.
Okay,
And this is a carboxylic acid, it's bigger than those with, hydrogen bond.
they would, they will, draw me a picture of it. Draw me a picture.
And then here we have an ion dipole.
Okay, that's good, that's good, that's really what I was looking for, okay? That's really what I was looking for. So, here's what happens with this one, okay? If we think about ion, so one of the types is ion dipole, okay?
Or charge, is that the same as charge induced dipole?
Charge-induced dipole, right, is different.
Okay.
Because that's a charge that's inducing a dipole on a molecule that doesn't have a dipole on it currently.
Okay.
Okay, so that's different. We think about solvation, or a solvation shell, okay? So, the polarity of water, the dipole, right, the direction of that is going to aim with the negative toward the sodium, and solvation is going to take place where the ion is surrounded by the oxygens from water, okay? So this is how ion transport really takes place in aqueous systems. We think about electrolytes, right? I mean, any of your typical electrolytes, you're drinking Gatorade, Powerade, whatever, this is this is how this is taking place, okay? There's actually a nice little video online, there's a few of these, and you can look at them. It's a real-time type video with salt crystal-like sodium chloride surrounded by water. The water comes in and it grabs one of the sodiums and starts shaking and hydrogen, or doing the ion dipole interaction, and it pulls it away. And then another one comes in and it pulls it away. And it's essentially showing you the sodium chloride salt dissolving in the water slowly over time. And then, same way with the chloride ion. What's the chloride ion gonna look like?
It has the hydrogens around it because it's attracted to the
That's right,
positive.
okay? So the hydrogen ions, not hydrogen ions, excuse me, the hydrogens from the water molecules will then be surrounding this as well, okay? So the partial positives lining toward the negatives and creating another type of solvation shell, okay? So that's ion dipole. What about this one? What about charge together? Now, Bridget, you're the one that drew just sodium chloride right next to each other.
Yeah.
But they're not gonna necessarily be next to each other, okay? They're gonna be more like this. But what about molecularly? On a molecule, how might you see charge on a molecule?
You could have positives and negative residues interacting like enzymes and when they're bonding.
Yes, amino acid residues, okay? So then you have NH3 plus on one residue, right? I'll just put like this. And then the carboxylate residue on the other side, negatively charged, okay? So two amino acids, and now we have a negative charge on this side and a positive charge on this side, and there's your charge between two different amino acid residues. Good job, Riley. Okay. Hydrogen bonding, the easiest one with that one is water. But we also see donor acceptor with residues too, just like what Caleb was talking about in DNA-based pairing, right? So we can see nitrogen, hydrogen to nitrogen, okay? So we can see hydrogen bonding here. So partial positive, partial negative. We can see oxygen, hydrogen. So these are donors, hydrogen bond donors, and these are acceptors. Okay. What else can you do? What else can you do? What other donors?
You could do water and amine.
Okay, so like that? Uh-huh, yep. Okay. What about a carbonyl? Did you do a carbonyl?
You have two carboxylic acids, the proton would be attracted to the carbonyl oxygen.
Like this, Caleb?
Yes, sir.
That's correct. Okay, so two carboxylic acids could be donor-acceptor relationships. Yep, that's also correct. Okay. Coming back to the carbonyl, okay. Donor, acceptor. Oh. these types of interactions literally keep us alive. They keep us alive. They keep all the little machinery in our bodies operating all the time and making biology work. Okay? They're very, very important for life. And I think that they are amazing, very specific. If you look on page 21 in your book, you'll see many of these types of interactions. I think the harder one for you to come up with was the induced dipole. The induced dipole is harder because it's harder to think of like how electrons could move to create a dipole. But if you think like something like the benzene ring, so on page 21 they show you the benzene ring. Benzene rings are electron rich, right? But even more important, they are resonance stabilized because the electrons can move around the pi cloud whenever they want, right? They're delocalized around that ring. So it would be like you in your happy environment, and let's say you're cozy and you're warm, and somebody opens the door and it's freezing cold right next to you. It's disrupting you, okay? You feel cold and you're like, shut the door! That's how this feels, okay? Benzene gets close up to something that's charged and it delocalizes. It moves its electrons in one direction as a result of that charge differentiation, right? So something gets close to it, the charge delocalizes and creates a temporary dipole, okay? So that's what charged dipole or induced dipole is. Everybody understand that? Is that a pretty good example how that might feel? Okay. The other one that is harder to deal with is the dispersion forces or London forces. These are your weaker forces. Okay. In organic chemistry, I describe London forces like you walking down a hall, and again, you're happy. You're walking down the hall, and you bump shoulders with somebody, and then you say, excuse me, and then you go right back to where you were at, okay? It's a really weak interaction that results in a change in dipole, but it goes right back to where it was at, okay? So that's London forces or van der Waals type interactions. Those type interactions happen in all molecules, but nonpolar molecules will specifically only undergo London forces or those types of weak interactions. Okay? And that's why their properties are very different from molecules like water or your alcohols. Riley?
Van der Waals and London force, is there a difference?
So, is there a difference? That's a great question.
I thought they were the same thing.
I'll have to look it up, but I think they're the same. I'll have to look it up. But
I've been told by some people they're the same thing, and other teachers have told me they're different things.
Okay.
And I've been confused about
Well, I think we can look it up. Hydrogen bonding is considered a special van der Waals force, okay? But it is very specific. It's very specific, okay? All right, so there's that dipole moment in water. And there is the benzene showing how the dipole moment can form. And I, again, like to think of this as hot and cold, or, again, electron rich or electron poor. You've got something coming up to the benzene that's causing the shift in electron density, okay? Whether or not it's benzene or something else, it's going to cause a delocalization of electrons. It's going to cause those to move, okay? Pi-pi stacking, right? Those types of interactions where you have dipoles that are induced in different directions and that they're kind of sharing their electron clouds, okay? That's a space-filling model of what that might look like. I really am not a big fan of space-filling models. I don't want to really go into van der Waals radii. There's the interaction of hydrogen bonding between a carbonyl, okay, where you have the donor and the acceptor. The acceptor is always going to be the one that has the lone pair of electrons on it, okay? So try and remember that. Your acceptors have lone pairs of electrons. Your donors have the hydrogen with the positive charge. Here's some examples of the donor acceptors. So these are some of the ones that we were drawing on the board. We did miss a couple of these. The really one that I thought was rare is the one down here on the bottom with the sulfide, the sulfur and the hydrogen. And they don't really consider sulfur being able to undergo hydrogen bonding due to the fact it's not electronegative enough to do that. But I think there's debate about what that actually looks like. Okay. We do see sulfur interactions in amino acid residues. We do see that. Here's an example of an alpha helix for a particular piece of a protein. Okay, so this is just a peptide that you're looking at that's wound in the helix. Why is it wound in this helix?
So it can hydrogen bond?
Not so it can hydrogen bond, but because of hydrogen bonding. Okay, so those interactions that you see between the residues in the vertical helix puts it into that spiral shape.
In fundamental stuff, you said it was more, that had more to do with the non-polar residues in the protein, trying to leave the water, but it's around it.
So, in terms of secondary,
In terms of forming alpha helixes and beta sheets. You said it had more to do with the non-polar residues trying to get away from the water.
I don't doubt that. I don't doubt that. But I think you can look at it from either side, right? You can look at it from the hydrophobic side or the hydrophilic side. I mean, maybe Riley, maybe that's the truth in the fact that you have your nonpolar here, and that what it naturally wants to do is to form those non-covalent interactions to shield itself from that hydrophobic, from the hydrophobic regions. Yeah, I think you can look at it from both sides. I would definitely say that's the case. When we come back, we'll finish up talking about some of this and go into a little bit more detail about hydrogen bonding interactions. But hope you guys have a great day.